In this example, we show how to use a Fourier series analysis to generate a magnitude and phase plot of the ECG signal shown below. ECG is electrocardiogram. And the sampling frequency here was 50 Hertz, so that has to be given in order for us to assess the data. So first of all, Fourier series analysis always requires that the waveform be periodic, so we have to assume that this ECG signal is periodic. Now, this is not likely, but it really doesn't matter because we don't know anything about the signal before or after the segment anyway. So basically, this plot on the previous page, and I'm sorry, this is an EEG signal, this is an author's misprint. This plot on the previous page is basically, although it does look like ECG, I'll have to clarify that. Plot on this page basically shows here's our signal, and so we've taken the whole data record length to be a period. So we're kind of assuming that this guy is just repeated, for an infinite time series. Okay, so under this assumption, we can implement the Fourier series equation to find the cosine and sine components using MATLAB, and we can convert those to a magnitude and phase equivalent, and then plot that. So we're going to make m be n over 2 because of the Nyquist sampling criteria. In other words, the highest frequency that we can represent with this signal is going to be half of the sampling rate. So 25 Hertz will be our highest signal that we can represent. So here's the Fourier series analysis. We're giving it the sampling frequency, loading the data, determining the length so that we can get n, determining the time so that we can get the period, calculating the fundamental frequency f1 from the period, and then when we get ready to plot, our time vector will just be 1 to n, and we divide by f sub s so that it converts it into seconds. So finding the magnitude and phase using the basic equation is shown here. Here are the a coefficients, here are the b coefficients, and then the magnitude is going to be the square root of a squared plus b squared, and the phase will be the inverse tangent of b over a. If you have not done a phase and magnitude conversion from sinusoids, then you can look that up because that's basically what this is doing. This is going from rectangular to polar coordinates. We then plot, and I will make a comment about this line in a bit, but when looking at the phase, it is important to use this unwrap command. And then this converts the phase from radians to degrees, multiplication by 360 and division by 2 pi. This plots the magnitude spectrum, this plots the phase spectrum. So the total time was determined, as we said, by taking the number of points and dividing by the sampling frequency. The fundamental frequency is 1 over that total time. The correlation with sine and cosine waves was performed, and then they were converted to a single sinusoid representation using magnitude and phase. The component frequencies are saved in a vector for plotting. Okay, so what are some potential problems here? The main potential problem is the issue with the phase curve. The issue with the phase curve is that basically you're taking theta as negative arctangent of b over a. So a lot of times, depending on whether it is the B or the A that is negative, there can be some ambiguity in the phase. So if the B part is negative, that means one thing. If the A part is negative, that means another thing, mainly whether the phase angle falls between 0 and negative pi over 2 or between pi over 2 and pi. So this could be either a negative B component or a negative A component, but it would technically be a different angle. So the A tan2 function checks the signs of both numerator and denominator and adjusts the angle accordingly. The other potential problem is what we call phase wraparound. Now phase angle is limited to plus or minus pi, but some frequencies the phase will exceed those limits. So what happens is the phase curve, they will say it wraps around. So you have a phase of pi plus theta or minus pi plus theta. So the way we compensate is you look for transitions that are greater than some threshold. And if it's found, you reduce that transition by adding plus pi or minus pi, whichever gives you the smallest transition. So in other words, you don't want angles greater than or less than, greater than 180 degrees or less than negative 180 degrees. So if you had like 240 degrees, you would want to adjust that so that it actually came out to be negative 120. So that's what this is basically saying. So what the unwrap command does is it makes the phase vary between plus and minus pi. So here is the result. Here's the magnitude and phase plot. So here's the frequency axis. Here's the magnitude of x. And this just shows you basically the max and min values of what the frequency plot looks like. So you can see in this signal we have a lot of 7 hertz. So clearly this is an EEG signal because we have a lot of 7 hertz kind of signals showing up here, and then some more, another peak out here between 15 and 20. Here's the phase plot as well. As a general rule, when we're doing analyses, unless we're looking for things like synchronous activity between two locations, we don't look at phase a great deal. We typically tend to look at the magnitude, and a lot of times, as opposed to looking at the magnitude, we'll look at the magnitude squared, which is known as the power spectrum. Okay, this just says that the Fourier series is invertible. So if you have the frequency components, and here's where the phase becomes important. If you want to get your original signal back, you can't do that from a magnitude plot alone. You have to have both magnitude and phase information. So basically, we can get that if we have both magnitude and phase. Okay, here's an example to find the Fourier transform of a triangular waveform defined below. We want to find the first Fourier transform components, reconstruct the waveform using the first 5, and then the first 10 components, and plot the reconstructed waveform superimposed on x of t. Make your sampling rate 500 hertz. So basically, we'll construct the waveform in MATLAB, decompose the waveform into 10 components using the approach featured in example 3.1. Then we'll reconstruct the waveform using the digital version of the inverse Fourier series equation. So we'll need to normalize by 2 over n. And note this waveform does not have, or does have, a DC term, which will have to be added to the reconstruction. So if we don't incorporate the DC term, this would be centered about the 0 axis. So we'll have to add that DC term in. So here is how the deconstruction is done, or the decomposition is done. Here's the cosine coefficients and the sine coefficients. And then here's the magnitude and the phase spectrum. So then we reconstruct the waveform by basically creating the Fourier series. And this for loop includes the first 5 in the Fourier series, the first 5 terms in the Fourier series. So then the system plots both the original waveform as well as using 5 and using 10 components. So you can see here's 5 components and here are 10 components. And notice this ripple. This is known as the Fresnel effect. Anytime we have a very sharp transition or edge, we're going to get this Fresnel effect when we try and reconstruct the waveform from its Fourier coefficients. The reason for that is to represent a vertical edge or a step, we need an infinite number of components. So you will never quite get a complete representation of this without this ripple present. Okay, it's important here to talk about symmetry a little bit. So definition of even and odd functions, as well as half-wave functions, but mostly in the class we want to focus on even and odd functions. So basically an even function says that x of t is equal to x of minus t, and an odd function says that x of t is equal to minus x of minus t. An even function will only have cosine terms in the series, and an odd function will only have sine terms in the series. Half-wave symmetry says that x of t is x of the period minus t, And so there, for even terms in the series, the coefficients are equal to 0. So here's an example of some symmetries. This is an even function, so notice that it reflects around the vertical axis. This is an odd function. Notice that it reflects around the vertical and horizontal axes. And then this is half-wave symmetry, which to me has always been just a little more difficult to see. Now the Fourier series typically, as we transition from the Fourier series to the Fourier transform, the Fourier series is typically written not as a sinusoidal sum, but actually as a sum of complex exponentials. So if we were to use Euler's identity, we can convert from coefficients that are sinusoidal and cosinusoidal to a single expression that does not involve sine and cosine, but that only involves complex exponentials. And so the discrete time Fourier series basically becomes a sum of these complex exponentials, and the time, the continuous variable of time, becomes the discrete variable of n times t sub s, where t sub s is the sampling time. And so finally, what you end up with is this form here, where you have capital X sub m in terms of the level of transform, which is, or the level of family member number or frequency, which is m. N is your sample number, which is related to time, and capital N is your total number of samples. So you go from an n variable, which represents time, to an m variable, which represents frequency. And so the discrete Fourier transform then, applying Euler's formula, you could get to a sine and cosinusoidal form if you wanted to, but this is usually not done. And the inverse Fourier series is just the inverse Fourier series equation is just the inverse Fourier transform in discrete terms. It can be written like this. So MATLAB and almost all other computational routines that calculate the Fourier transform use the complex form of the Fourier series.